Okay, here we go again for the third and final stream of the day. We are in the programming class. We have made it all the way to chapter 6 of the Koenig and Ritchie textbook, which means that we're today going to be learning about structures. So this is going to be the basis for all kinds of data structures, and this is very similar to how you will be working in object-oriented programming later on, where you will be combining both data and functionality. Today, what we're doing is we're binding together data into a single entity so that we can have a variable that actually combines things like, for example, a username and a password and an account balance and such in one single thing, instead of having to manage several fragmented, separated entities of data. So the first example that the book authors are using for a structure is taking a two-dimensional point that has an x-coordinate and a y-coordinate, and then defining a structure that says that we're going to make a point, and the point's going to have an x-coordinate and a y-coordinate, and both of these are going to be integers. So now these things, we can call them fields or members, and the whole thing, it's a structure. Some people actually kind of call those objects, even though it actually really isn't. It's just like a combination of things that go together. Okay, so now it means that I can make variables that have a type struct point. If I don't like having to type struct point, I could use a thing called enumeration and a type def to kind of like make new names for my data types so that I don't have to call them so complicated. We're going to try that type defing thing later on. And when I want to access the fields, the members, I can use the point. So if I have a variable pt, that's a point, pt.x is going to be the x coordinate and pt.y is going to be the y coordinate. So then I can just write my program where I'm operating with these points. Then I can also make a structure that's actually combining other existing structures. Like if I have one structure that defines a point, I can now make another structure to define a rectangle. Because if I say the point that this is my lower left corner and this is my upper left corner, I can define a rectangle by defining the diagonally opposite corners, the points. So I can make structures of structures and structures and such. So this is lovely. What I can also do is I can make functions that work with structures. I could technically build a structure inside a function and then return it. Or I could pass a pointer to a structure, to a subroutine, and then that subroutine could do things to it. I can, of course, make regular subroutines as well, like take these two structures and do something with their values. But if I want to be able to change the structure, it's just like always before, I need to be passing the pointer to be actually able to change what's inside that structure. Once I've defined my structure, I can make an array of structures very easily. It's just like making an array of integers, except now every single element is going to be a structure of that one same kind. So this is extremely useful. You could make like the list of people signed up for a class or something else by putting the things in your structure into an array. When we're reserving memory for a structure, it's very important to use the size of operator to figure out how much space do I need for this structure. Because if my structure contains, let's say, a 5-string character, 2 integers, and a floating point number, it's going to be a little bigger, and it's not obvious always how many bytes I need. So I can ask size of, and then the name of the type, to ask C, how many bytes is this going to be? So I can just use the size of to ask how big are the structures going to be. Now we can take a tiny little look on the first little homeworks so that we can see if we have correctly understood what's going on here. I'm going to take a little screenshot of the first question in exercise 6. And remember, these are my values. You guys are going to have slightly different values. So what's going on in this first little code here? I am defining, sorry, let's make it bigger. I'm defining a structure. It's going to be called account. I added that type def thing in front, like I was saying before, so that I don't have to type struct account. Instead of typing struct account, I'm just going to type ACC. Like ACC is the nickname to struct account. Every account is going to have a username, which is a string, and a double floating point number, which is the account balance. Then I have a transfer. I need to tell it which account I am transferring from, which account I am transferring to, and what's the amount of money that I am going to transfer. So if I want to make a bank transfer, the first thing I need to check is there enough money on the origin account not to empty it? I don't want to empty it. I need the balance to be larger than the amount. Technically, I could allow an inequality here if I allowed people to have empty balances, but I don't want to. So if the account that the money is coming from has enough money, then I add the money to the destination account and remove it from the original one. If there isn't enough money, I won't do anything at all. Let's try, see if this is okay. Can you guys vote green if you understand what the struct account does and what the void transfer method is doing? Remember, you can vote by typing in Discord exclamation vote green. I'll show you guys how, because this is kind of new. You could vote like this. If you're not entirely sure, but you don't have a question, vote yellow. And if you do have a question, vote red. If you want to clear your vote, you can type something like vote clear. If you don't want everybody to see it, then you can go message the bot and you can just vote by private message. If you haven't given the bot your Discord username and student ID, and if you're not registered on my website, you could also vote on the web. But it's the easiest way for me to know what's going on when we're actually voting. Okay, so just a little recap here. We're defining a structure. If I didn't have the type def and the ACC, the variables would have to always be called struct account something. But I made a new data type nickname, ACC, so that instead of having to type here struct account, I can just type ACC, it's briefer. So I've made a bank account structure, and then I've made a method for transferring money from one account to another account. And that only happens when the origin account where the money is coming from has enough of a balance. So I can take the money out of there and put it to the other account. That's what's going on for now. Then I have a second little subroutine that just prints out the username and the balance. So now we can see both types of notations here. When I have a pointer to a structure and I want to access a field, I have to make this little arrow. When it's not a pointer, when it's the structure itself, I use the dot notation like the book mentioned. Both of these are also mentioned in our reference card here. If we look at the reference card and we look at the part about structures, I can create the structures, I can access the members, and if I have a pointer, I use the little arrow to access the member. And if I access first the address pointed to by the pointer to the structure, then I could use the .x. So I can either write this or I can write this for the same exact purpose. So this little exercise here is showing both, because this method gets a pointer because it needs to modify the amounts. And if I don't give it a pointer, it can't modify because it's going to have local copies like we thought last time. But this one, it doesn't have to modify anything. It's only showing us things. So it's not getting a pointer. It's just making a copy. And then it's printing the username of the copy and the balance of the copy. So what's going on in the main? I am creating new accounts. I'm creating an account A, username is foo, and I am creating an account B, username is bar. In the beginning, my A is going to have $200 and my B is going to have $40. Then I am going to make a pointer to which is the account that has a higher balance, A or B. How do I know? I'm going to check if the balance of A is higher than the balance of B. Then the high account pointer has to point to the address of A. If A doesn't have a higher balance than B, then the higher balance account pointer will point to B. And the same way, I am making a pointer to the lower balance account. If A has a lower balance, low is going to point to A. If A doesn't have a lower balance is going to point to B. Then, when I know who has more money and who has less money, I'm going to calculate the difference in their balances. I'm going to take how much money does the rich one have, and I'm going to subtract how much money does the poor one have. And now I'm going to do social balancing. In the homework, you need to think, what do you have to put here instead of the 3 dots so that the two accounts end up having the same amount of money? So my A has $200, my B has $40. So my high account will be account A, my low account will be account B, and the difference between will be $160. So now I want to transfer some from A to B so that A and B end up having the same amount of money. Let's play with this for a little while. I'm going to take this code, going to find my terminal. Let's go to the repository. And let's give this a name. Homework 6-1C. Let's make a file and put that code there. And now remember, my A was going to be $200 and my B was going to be $40. You have to remember to put your own numbers there. They're not necessarily the same ones as mine. So let's try this first without transferring anything at all. I could actually add here also return 0 if I want to, so that the compiler doesn't whine about main returning an integer. I'm going to compile this particular file and I am going to run it. So if I didn't make any transfers whatsoever, in the end, A still has $200 and B still has $40. If I make a transfer from the high account to the low account of an amount of, let's say, $20, and I compile and I run, now I've transferred $20. But I don't want this to be a fixed number. I want it to be so that even if I randomly generate a number here and randomly generate a number here, it will always end up putting the same balance in both. So how much do I actually have to transfer? I would need to transfer something that's related to the difference, right? But if I transfer the difference as such, I don't end up with the same amount in both accounts. What happens if I transfer half of the difference? If I transfer half of the difference, I end up with the same amount of money in the high account and the low account. This should be mathematically semi-obvious, okay? I'm not gonna upload the solution as such. I'm gonna at least make people watch the video. So let's upload this to the repository. I can't type today. I can almost never type. Okay. No, push, push, push. Thursdays are so hard on my brain. So that's the very first one. The point is to transfer half of the difference from the high account to the low account. Can we please vote green? Again, I'm resetting the votes if this is fine. And please, please, please also do it on the website so I can see on the results that you guys have responded this question here in the column for E6. This is a very good way to check whether or not you actually understood anything about what I've been saying about structures, because it doesn't make a lot of sense to continue discussing these structures if we are confused about how they work. And this first exercise, it shows us all the basic stuff because it shows us how to make one, how to modify it using the pointers, how to look at its values just using the dot notation for the fields, how to initialize one, how to make a pointer to one, and then how to interact with the whole thing. So this little thing has been designed specifically to show you all the relevant elements of playing with a structure. One person's fine. And they have their point, they're not lying. Okay, that's very nice. If you need a little bit more time, please vote yellow so I won't keep going. If you simply want to do this now because you're otherwise occupied, you can vote gray and I won't wait for you. Then for the second program, this I'm going to let you guys do on your own. What's going on here is that you need to make a memory allocation because this thing will be putting numbers into an array. We can see here that it's going to put a total of n numbers into an array. Then it's going to call a sorting routine from the standard library using a comparison routine that we've defined here to sort the data. And after the data's been sorted, it's going to print out information of the data only if the data is different from the preceding data. So here there is a free for liberating the memory, but nowhere in this code I'm reserving the memory. So when we're reserving the memory, we need stuff like what we're looking at in the book right now. We need to do something that has to do with the size of, and we need to do something that has to do with a malloc to reserve some memory. So we are interested in reserving space, finding it on the reference card for you guys. Here, storage allocation. We're actually just going to be using this one. We're going to use a malloc, and you need to tell the malloc the size of the thing you are reserving. And when we look at this code, we can easily tell it's going to be n integers. So if we want n integers, first we need to figure out how big are ints. So we're going to use the size of that I just mentioned. And then if we want n integers, we're going to use the size of the integer, and we will multiply that by n. We will give this as an argument to the malloc, and then we want to tell malloc that the thing it's going to give to us we want to use it as a pointer to an integer because it's going to be an array. So we're going to recast it as an int pointer. Something of that nature. So that's all that's happening in that one. A very lovely thing we can do with structures is that I could make a structure that has a field that is that same structure. So I could make stuff like trees, where I could say that a node has a left child and a right child. And the left child is a node that has a left child and a right side. So I can make recursive data structures using these structures. And we already have a code here for binary trees. We can look at that code. I'm not going to go into too much detail about it because last year they found it kind of unsettling. It's a very important thing to deal with at some point, but I don't want to push anybody too hard. So go in your own rhythm. Let me hide some of the background stuff so it's a little easier to read. So what I'm saying here is that I want to make a type definition for a structure called tree node. Its fields are going to be a character value, an unsigned integer counter, and an unsigned integer depth, referring to the level in the tree. It's going to point to a struct3 node that's going to be a left child, and another one that's going to be a right child. I'm going to call these things nodes. And then I can make subroutines like let's get rid of a node, or let's insert a node. This is a lot of code. You guys don't have to read all of this. Or show me a node. Or show me them in alphabetical order. And then I've made this little program here that if I type a dash, it's going to erase the tree. If I type an exclamation, it's going to show me the tree. If I type an interrogation, it's going to show me alphabetically the tree. And in any other case, if it's not a space, it's going to try to insert that thing into the tree. Let's look at this for a little while in action. I am compiling it and then I'm running it. So I want to put stuff in the tree. Let's put A, B, C in the tree. Okay. I want to look at the tree. I have an A. From that A, I have hanging a B, and then from the B, I have hanging a C. Okay, let's erase the tree. I'm out. Let's do this again. So now I'm going to make a hello. What does this look like? I have an H. From the H to the left, I have an E. From the H to the right, I have an L. And then from the L to the right, I have an O. I have to go to the whiteboard so we can grasp what's going on here. So these letters, they're arriving one by one. I'm putting them into the structure. And when we analyze the code, we can say that whenever we get a letter, if it's before the current node in the alphabet, I'm going to be sending it to the left side. And if it's after, I'm sending it to the right side. So H arrives first. I have one H. Then I get an E. E is before in the alphabet. It goes to the left. Then I get an L. It arrives here. It's after in the alphabet. It goes here. Now remember, I have one H and one E and one L. Then I get a second L. It goes here, but since it's already present, it just updates the counter. Then I get the O, hello, and the O goes here. So this is what my tree is looking like. I have a node that depends, has children, has dependent children, this node and this node has another one. The ones that don't have children, they presently have null pointers, pointers that are not pointing to anything. I am adding more nodes. I am adding everyone. So what does the tree look like now? Let's do this manually first. Adding the E from everyone. Let's say everyone. This E comes, it goes down here, it makes a 2. The V comes, it goes all the way down here, it makes a V. Another E comes, it comes down here, it makes a 3. R is going to be before V, but after O. Then we're going to get a Y. It's going to be after V. Then we're going to get a new O. So we're going to update the O. Then we're going to get an N. N is before O, but after L. And then we're going to get yet another E. So the E is going to go here. So this is what we're supposed to be getting. I'll take a picture of what's on the whiteboard so we can compare. So I have an H at the root of the tree. To the left of it, there's an E, there's 4 of them. To the right of it, there's an L, there's 2 of them. To the left of the L, there's nothing. To the right of the L, there's O, there's 2 of them. To the left of the O, there's one N. To the right of the O, there's one V. To the left of the V, there's one R. And to the right of the V, there's one Y. And then if I want to run the structure in alphabetical order, I had a function for that as well. We have an E, it comes in the alphabet before the H, then we have an L, then we have an N, then we have an O, then we have an R, then we have a V, and then we have a Y. So all of that functionality is in this code bintree.c, which is simply me extensively interacting with this structure that I'm calling node. For example, when I'm getting rid of the node, I'm saying, okay, if this position exists, I'm going to erase the children first and then this position. So when I'm erasing the tree here, it's first going to erase the R and the Y, then it's going to erase the V with the N to be able to erase the O, then it's going to erase the L and the E to be able to erase the H. When I'm inserting values, what am I actually doing? When I'm inserting values, I am checking in the current position. If there's nothing there, I'm making a new node and I'm putting the value there, and the counter is going to be 1. If there's already something there, I have to compare the value. If the value matches the letter I wanted to add, I'm just going to increment the counter. If it doesn't match, then I need to go to a child that corresponds to the direction. But if the child doesn't exist, then I'm going to create a new node there. When I'm showing the tree, I'm doing something very similar. To show the tree, I need to show the children, and then I need to show the node itself. I'm putting a little minor sign in front of the left branch and a larger sign in front of the right branch to distinguish. And I'm putting a hashtag in front of the ones that don't have children anymore. And when I'm doing this alphabetically, I am going to first print the left child, then print the node itself, and then print its right side so that it comes out in alphabetical order. So that's all that this code is doing. I am not going to make you invent this, but your homework is going to be extremely related to this code. So you're going to first study this one. Then you can also study, if you want to, the bin tree 2. The difference between the first one and the second one is that in this one, in addition to be able to insert, we can also eliminate. And I think there are still possibly a couple of bugs in the elimination. Elimination is much harder than inserting. So I've written the code here to start getting things out of it. The good thing that we have from this code is that it's showing us how to use an enumeration. So I can also define, in addition to structures, I can define these other data types. This thing, it's an enumeration. It has two different possible values, agregar and borrar. And the name of the type is going to be estado. So this state variable, it can be in one of two states, add or remove. So instead of having to make a define, this thing is one, this thing is zero, and then using an integer and the defines, I can make this enumeration if I want to use like text to refer to the possible values. So now this program, I might be in two different states, the adding state or the removing state, and I can use the asterisk to switch from one state to another. Let's try to compile this to see how broken it is. Okay. So let's add some stuff to the tree first. Looks fine. Then I want to go to the removal state. Let's remove the S and the A and look at the tree. So now I just have the Eli left. The S and the A, they were removed. Then I could state again and to the adding state. So then now I actually have a tree corresponding to the letters of Elizabeth. And then we could look at that alphabetically. Or I could remove things again. We could get rid of the Abe part. We could look at what it looks like now. And now remember, I had two E's, so I just removed one of the E's. So that's why there's still one left. If I want to remove the other E as well, I have to remove again, and then there's no E left anymore. And then I could just print them alphabetically again, and I could leave. So it's a little bit messier to remove things because other stuff depends from there. Like if I were to remove here the L, I need to move this O to hang from the H instead. And if I remove the O, then I need to kind of figure out what am I going to do now, because I can't put the N to the left of the L because it's going to break the alphabetical order. So removing isn't so easy because you kind of need to figure out who's going to go where after a removal, whereas adding is really easy. You just kind of spill down the tree following the alphabetical order. You go left if it comes before, you go right if it comes after, you increment the counter if you find it, and if you haven't found it, you just hang it to the bottom. Okay, so the little exercise number 3, it has to do with this enumeration stuff. So what we're going to be doing in this third one, making a little screenshot for you guys again. We are going to first make some definitions. Read's going to be 0, 1, write's going to be 0, 2, execute's going to be 0, 4. And then I'm making a type def enum that has a false and a true, and that's going to be called Boolean. So I can make a variable of type Boolean, and that can only take values false and true. And I can force them to have the integer values that I want them to have to make them kind of compatible with how C works. So then I can do stuff like here. While done isn't true, we're going to be doing a switch case. What's the switch case operating on? On the positions of a string, which is y. What is y? Y are the command line parameters like we spoke the last time. So it's going to be visiting the command line parameters Ignoring the first one, we know that the first one is the name of the executable. So we're going to look at all the other command line parameters, each one at a time. If the first letter is a end of string, that's going to be true. If we have an R, we're going to make the status, which is here an unsigned integer. We're going to make it a logical OR with the read, which is 1. If it's a write, we're going to do a logical OR with the write, which is 2. And if it's an X, it's an execute, we're going to do a logical OR with the 4. So now these are essentially bit positions. So if the person on the command line says RWX, we are going to create a 111 bit string, which is going to be the integer 7. If we only want execute and we don't want read and write, we're going to end up with a 100, which is going to be a 4. So basically, these are integer representations to file permissions. Then once we have looked at the first position, we're going to look at the second position and the third position until the string is done. And if we put more R's and W's and X's, then it should be entirely fine. So let's try to work with this program a tiny little bit too. I'm going to go get the code. Because the program is complete. You can notice that there's nothing missing from the program. What we need to do is provide the arguments that make the program print a certain thing. So let me make this program just in a larger window. Wonder if it's already in the repository. Let's go see. I don't think it's there. No mention. So let's make it. It's going to be homework 6-3. Putting all the code there. Compiling it. No, this is not compiling it. This is running it. Sorry. This is compiling it, and now I'm running it. So if I don't give any command line arguments, it's not going to say anything. If I tell R, it's going to say 1, because that's the 0, 1 here. If I do a W, it's going to say a 2, and if I do an X, it's going to say, sorry. If I do an X, it's going to say a 4. And like I said before, if I do RWX, I'm going to get a 7. Why am I going to get a 7? I'm going to get a 7 because it's a 1 plus 2 plus a 4, because I am doing logical ORs with the bits. A 1, it's really a 0, 0, 1. A 2 is a 0, 1, 0. And a 4 is a 1, 0, 0. We talked about binary numbers before, so we should be okay with that. So how do I make a 3? A 3 would be a 1 with a 2. So an R and a W, that's a 3. How do I make a 5? It's a read and an execute. How do I make a 7? A 7 is the read and the write and the execute. Now all I'm missing is the 6 from in between. How do I make a 6? A 6 is a write and an execute. So if I provide these command line arguments, I can make it say 3, 5, 6, 7. Now just make sure that you make your numbers, not my numbers, in case your numbers are a little bit different. I haven't logged in, so I can't actually grade. Let's log in. Okay, mine asks for 7, 2, and a 4. So let's do this again. 7 is 1 plus 2 plus 3. 2 is just the 2, and the 4 is just the 4. So 7 to 4 comes from RWX, W, and X. And I have 1 point. Okay, so let's please do this. I'm going to reset the votes. Vote green if you manage to do it. Vote yellow if you need more time. Vote gray if you'd rather do it at some entirely different time. Just remember, you're putting here the letters. Every command line argument is going to turn up as a different number. To get a 1 in your sum, you're using the R. To get a 2, you're using the W. To get a 4, you're using the X. And we are simply making sums of these numbers. And how do I know that there are 1, 2, and 4? Because here it says read is 1, write is 2, execute is 4. Whenever I see an R, I'm ORing a read. Whenever I see a W, I'm ORing a write. And whenever I'm seeing an X, I am ORing the 4. So that's what I'm doing. So let's try this for a little while. See if we get it. And if you get it, it kind of means that you've understood what I'm doing here with this stuff. Really, the part about the enum is very simple. It's just the flag for termination. Not a very complex thing. And for some reason, I closed the homework page. I didn't mean to close it because we still need to look at it. And now I'm opening the wrong pages here. While you guys finish, I'm just going to dig up the homework again. Okay, I think I only have one person listening to me at this point. And I think that that one person is okay, so we should be able to continue. Let's take a quick look if there's anything else we really need to know in the book. So your homework is going to be related to this tree stuff. So it's very important to read well until section 6.5. Also remember to look at my code bintree.c in the GitHub. I'm going to give you guys the link just in case. Just in case you haven't seen it in a while, I'm going to give you the entire chapter 6 link. So carefully read all this. Study my code. Don't try to write yours before you've understood the section and you've understood what my code is doing. You don't have to worry too much about section 6.6. We're not going to lose sleep over it. The type def part that I'm using a lot so that I don't have to type the struct something, that I just type whatever I want instead of struct something. I'm using a lot the section 6.7 stuff. So please read that too. It's unlikely you really need to understand unions at this point. And this bit field stuff is kind of related to the mini exercise we're doing now. What's this number? 6.9. So if you have questions about that, you can check the 6.9. And then next week, we're going to start doing something that you've been waiting to do the entire time. We're going to start reading and writing files. So instead of us typing things as input and us printing things on the console, we're going to be reading stuff that's in a file, and we're going to be writing output into a file. So that's, at least according to me, that's extra exciting. We're still waiting to get a point on the third question. Remember, I'm leaving you the second question to figure it out on your own, but I practically already gave you what has to go into the answer, so that shouldn't be difficult either. But I'm going to wait for there to appear a 2 here before we proceed to discuss the homework in any more detail. I'll just give a little bit more hints here. If you type an R, you're going to generate a 1. If you type a 2, you're going to make a W, you're going to make a 2. RW in any order will result in a 3. X will result in a 4. An R and an X in any order will give you a 5. A W and an X in any order will give you a 6. RWX in any order will give you a 7. And there are no other numbers you can make. So basically, if you need to do 1, 2, 3, 4, 5, 6, 7, you're just going to write these things in that order. Now I think I missed one. RW, RWX, RX, WX, RWX. And if you need them in a different order or a different subset, just put them in that order. And you put only the command per line parameters on the answer. You don't put the a.out stuff, only the parameters, and you grade, and it should work just fine. And if you really want to know why, you're going to carefully read section 6.9 after you make sure that you understand binary numbers. Because if you don't understand binary numbers, none of this makes any sense. Because I'm basically making logical ORs with the bit string 001, 010, and 100. And when I make ORs between those, I can raise the lowest bit by making an OR with the read flag. I can raise the middle bit by making an OR with the write flag. And I can raise the left bit by making an OR with the execution flag. Khair, where's my number 2? It's kind of like having private tutoring on Twitch when nobody else in your class is participating. But it's also a lot of pressure because your professor refuses to continue while you don't finish the homework. If it's telling you you're doing it wrong, just tell me what the numbers are and we can figure out why it's wrong. Yeah, you're not adding any code. Yeah, you're just typing in what are the command line arguments. Let me show it here again. Make this a little bigger. So basically, if you want to make it type out 1, 3, 5, you would just put the command line R for the 1, RW for the 3, and then RX for the 5, and it's going to give you 1, 3, 5. And the part that goes in the homework answer are the command line parameters, the R, RW, and RX. So without the name of the executable, the stuff that I have highlighted in gray here, this is the stuff you need to write in the box. These thing is. So that it prints out the numbers, it's telling you. Yeah, it's just look at your own homework. In your own homework, right here underneath the code on top of the box, it says what are the numbers that you're supposed to make. Everybody has different numbers. So if it says 3, 5, 6, 7, then what do I need to do? I need to make the 3 as an RW. I need to make the 5 as an RX. 6 would be a WX, and 7 would be RWX. But you probably have different numbers. So just look at your numbers and think about how to make your numbers. We have all the time in the world. And the letters, they're basically just sums. So an RW, it's 1 plus 2. An RX, that's a 1 plus 4. Whereas the WX, that's a 2 plus 4. And the RWX, that's a 1 plus 2 plus 4. Okay, we have 2 points. That's so nice. Okay, so let's look at the homework. What are you going to program to make sure that you actually understood what's going on here? You are also going to make a tree, much like the tree that I put on the whiteboard. My tree had letters in it. Your tree is not going to have letters in it. It's going to have usernames, but it's also going to be alphabetical. So whereas I only had one character in my nodes, you're going to put a string, a character array in your node. All inner nodes need to have a left child and a right child, so meaning that active usernames can only be in leaves, whereas the inner nodes are going to be routers. So that makes erasing so much easier, because if I need to delete a username, I'm only erasing the leaf. I'm just gonna leave the router there. I'm gonna show this in a little bit on the whiteboard. So the reason we're making the inserting a little bit more difficult is to make the erasing so much easier. If somebody's trying to make a username that's already in use, we're just going to keep them asking for username until they pick one that isn't in use. We don't let two people have the same username. When they pick one that isn't in existence yet, we insert it to the tree as a new leaf node. When they deregister, they get removed. When they manage to create their user registration, they will need to set a password. And then if they want to deregister, they need to be able to provide the correct password, or the deregistration will not be done. You are not allowed to write any code before you've posted on Discord a picture of what you're planning to do. It's probably going to be similar to what I'm going to do on the whiteboard soon. So please try to draw first. Once you've drawn and I kind of think you've got the hang of it, then you can start programming. So let's look at this on the whiteboard for a tiny bit. And remember, you can use whatever's in the book, section 6.5, and my codes in the bin tree and bin tree 2 as a basis, but yours is going to be slightly different. But let's go to the whiteboard. Okay, let me get rid of this one. So in the beginning, you have absolutely no users. Then this person shows up and says that she wants to be Elisa. She just wants to be that. So we're going to create a first node. As there wasn't any nodes, there's no conflict, so that's fine. Her username is Elisa and her password is cat. This is our tree. There's nothing else there except Elisa and cat. Now, another person shows up. This person wants to create an account. He wants to make his username Matt. So we're going to check with this node, and this node says Elisa. Elisa isn't the same as Matt, so we're fine. We can add Matt. But the problem is that the users are only supposed to be in the leaf nodes. So what I'm actually going to do is I am going to make this one a router node. It's not going to have a password anymore. And I'm going to put Elisa alphabetically to the left. So Elisa with cat is going to go here. And the new user, Matt, because M is after E in the alphabet, Matt's just going to go here, and he's going to have another password. His password is going to be computer. Okay. So now another person is going to register. Alberto is going to register. He wants to use the system too. So we're going to check in the root. Here is Elisa. Alberto comes before Elisa in the alphabet, so we have to go in the left branch. And this is a user node. So again, we have to turn it into a router node and make a copy. We have to move the Elisa and we have to move the Alberto to the children. But now the problem is I need to put Elisa on this side and Alberto on this side. And here I need to put something that tells me that alphabetically we're going to put the same or equal to the left and the larger to the right. So Elisa has to go to the right. So this one is actually going to end up being Alberta. So that we know that if we want to find Alberto, it's before Elisa in the alphabet. It's before or equal to Alberto in the alphabet. It's going to be here. So the Elisa cat ends up here, and Alberto's password is going to be tooth. It's going to end up here. So now I have 3 users, Alberto, Elisa, and Matt. So now let's say Elisa doesn't want to have an account anymore. Elisa says, I want to deregister. So we're going to first check, where's the user Elisa? It's going to send us here, and then it's going to send us here. When we go here, it's going to ask us to confirm the password. If Elisa doesn't know that the password is cat, we're going to refuse to erase. If Elisa knows that the password is cat, we're going to erase this user. Then we're going to notice, oh no, this router node doesn't have 2 children anymore. It was mandatory to have 2 children. So what are we actually going to do? We're going to get rid of this router node because it's not necessary anymore. And Alberto is going to be hanging straight from this router node. So now we have a router node that's called Elisa, but it's not a user anymore. If Elisa wants to register, she will be sent here. She will be sent here. And then this Alberto node will notice that, hey, I need to split. I need to make a split here. Obviously, we could draw the Alberto node a little higher first. Alberto and Tooth are here. So if Elisa wanted to register again, this would make 2 children. It would put the Alberto on this side, Elisa on this side, and this would become a router. Okay, so let's say that now Lindsay wants to register. If Lindsay wants to register, we go here, L comes after E, then we go here, L comes before M. So then Lindsay needs to go on this side. And since there cannot be users other than at the end nodes, it means that we need to make this one into a router node. We are going to move Matt computer on this side, and we're going to put Lindsay dog on this side. So now this one's going to be a router node. And that's what we're going to be doing here. We're just going to be creating new nodes always at the end of the tree. If it needs to go somewhere where there's already somebody, we're going to split into 2. We're going to put the smaller of the 2 usernames in alphabetical order into the router node. The router nodes are not going to have passwords. That's how we know that they're router nodes. And when we are erasing, when we erase, if there is a brother node, then the brother node needs to take the parent router's place. So what's the structure going to look like in code? Let's take a tiny little look at what's this going to look like. Taking a picture of the whiteboard first. So we're going to need to make something like typedef struct system user. I could just actually make it, yeah, I'm going to need to give it a name, system user. And what's going to be inside that structure? there's going to be the username, and there's going to be a password. Then there is going to be the left child and the right child. That's going to be struct system user pointer left child and a struct system user pointer right child. And this whole thing, we're going to be calling it user. So something like this, roughly like this, will be going on. Then how do I know that something is a router node? If the password is null, then it means it has it's a router node. And if it's a router node, then the left child must be valid and the right child must be valid. And the actual users will always be represented by leaf nodes that are not routers. Those fields, the left and the right children of a leaf node, they will always be null. So when we insert, and we want to go left if something is less or equal in alphabetical order. How do we know if something is less or equal in alphabetical order? We can use the comparison operator for strings. The strcmp will work wonders for that. So if that gives us a smaller number, we're going to go left. Otherwise, we're going to go right. And when we are creating, if nothing exists, we're going to create a single node. That's the only thing in the tree. And if something exists, we need to create a router node. We're going to first create a router node to substitute the position where we want to add stuff. And then we're going to hang the existing thing on one side of the router and the new stuff on the other side of the router. And which one goes where depends on the alphabetical order. So we need an if here. And then we're going to put the username of the smaller one, the alphabetically smaller one, as the username of the router node. Okay? And when we are removing, we first search where should that user be. If we find a matching user node, we ask for the password. If the password matches, we're going to remove. And when we are removing a node, it means that the sibling node, like if we're getting rid of the left side, then the right side needs to go in place of the previous father router. And if we're removing the right side, then the left sibling needs to go in place of the previous router. This is a little bit complex. It's not impossible, but it's a little bit complex. So it's really important you think about this before you start programming this, because you're going to make a literal clusterfuck if you don't actually think about what you're doing. And don't try to make both things happen at once. Just first make a tree with just the usernames. Don't think about the passwords, just add usernames. Then when you're able to add the usernames, then think about also including the passwords. Then when the usernames and the passwords are fine, everything's working fine, then start working with removing things. And you can get quite a lot of points with even a partial attempt, as long as it's your attempt and you've been working on it on your own, that's fine. And with just a decent picture of what you're planning to do, that's already going to be a point. So no stress. Post any designs or questions on the channel. If it's more or less working hours and I'm not giving some other class, I will respond to you very quickly. And I will see you guys next Thursday to see how far we got with implementing this tree. And then we're going to go over chapter 7. That's going to be the last chapter where there's actually straight up homework. We're going to learn the file handling things, and then we're going to start defining the project topics. Everybody's going to be doing an individual project where you first design a program, explain us what it's going to do, and then you actually implement it and you do a demonstration of the code working, and that's going to give you quite a bunch of points. And then we're just going to practice for the final exam, and then we are going to be done. So any help you need, please write something on the channel. I will be staring at it for the next hour in case there's any questions, in case there's any confusions. Remember that everything we need to do, it's here in this book. It's not a long book. We are on page 150 right now. It shouldn't take you a long time to read from the very beginning if there's something you've missed. And when you revisit earlier chapters, stuff that used to sound complicated starts to make sense because you have more practice now. So it should be a little bit easier to understand. So any trouble, any questions, you will let me know. And I am eager to wait for any kinds of diagrams and plans on how you're going to be implementing this. I'm interested to see what your structure is going to be like, what kind of subroutines you're thinking of, and how are you going to make sure that the functionality we are trying to go for will actually be reached by your plan. In about a minute, I'll be posting the link to this class on Twitch, and I'm also going to export it to YouTube so it doesn't disappear too quickly. Take care of yourselves and get the vaccine if you live in San Nicolas. It's today and tomorrow still. For 20 to 29-year-olds in San Nicolas, it's very important to be vaccinated. I'll catch you guys next week.